Alrighty, roller coaster problem. So we have this roller coaster with this ridiculous height of 215 meters. And we want to get the speed of the roller coaster at the bottom of the loop right here. I gave you a little bit of extra information there. That 25 meters is nice to know for later parts of the problem, but we don't need it right here. So we have all EG at the top, and then we have EK at the bottom. So we can set up our conservation. If you want to do bar graphs, it's like we have all EG here, no EK, no E elastic. Some people got really sassy and decided to do this. So we have EG, and then we have EK here, and then some elastic energy, and then we draw the little bar for dissipated, but there's no dissipated energy. It's exciting. So EG equals EK. All right. So then we're going to have MGH equals 1/2 mv squared. Now, some of you use the 500 from down here to solve, but it turns out we can actually divide both sides by m, which I'm going to do here. So we have 10 times 250 equals v squared divided by 2. So that's going to actually get me that 5,000. Yes. 5,000 equals v squared. When we take the square root of both sides, we're going to end up getting, let's just see, 70.7 meters per second. Well, isn't that just a wonderful answer to a wonderful question? Did I get that right? Yes, I did. All right. Now, we want to know the normal force on the roller coaster at the bottom of the loop if its mass is 500 kilograms. So let's draw that free body diagram. We got the normal force pointing up, and we have the weight force or the gravity force pointing down. These two forces are not in equilibrium. They actually have the effect of making the car move in a circle. So we have Fn minus Fg, and the effect is that we get mv squared divided by r. So we have Fn minus, now Fg is going to be 500 times 10. Let's be careful here. Fg equals m times g. That's going to be 500, and then you times it by 10. So that's how we get 5,000. And that's going to equal 500 times 70.7 squared all over our radius, which is 25. So let's work all this out, and we'll end up, we're going to get a pretty big normal force here, just to be clear. So when we actually work this out, this is going to end up being I ended up getting, whoops. Let me just double check this one more time. So I'm getting 500 times 70.7 squared divided by 25. Yep, plus the 5,000 here. So I'm getting about 105,000 newtons. That's pretty big. I don't know why I said it like that. That was ridiculous. Okay. Oh my goodness. Now we want the value of the normal force on the roller coaster at the top of the loop. So let's be careful here. we're going to say mgh. Or what we can do is this. We can say EK or EG at the top of the roller coaster here equals EG plus EK at the top here. And we'll go ahead and actually set up those equations. So EG equals EG plus EK. And what I'm going to do is I'm going to use a little bit of algebra. So I have mgh equals plus 1/2 mv squared for the kinetic energy. Now let's talk about this EG at the top of the loop. If I go here, this height is actually twice the radius. So this is going to be m times g times 2r. And now I can put in some numbers. So 500 times 10 times 250 equals 500 times 10 times 2 times r ends up being 50 plus 1/2 times 500 times v squared. So let's multiply a little bit of this out. I'm going to get some big numbers. So I'm getting 1,250,000, man. I'm sorry, that was, I don't know what that was. Okay. And then 500 times, all right. Am I getting 250,000? Jeepers. It's a pretty big number. 250,000 plus 250 v squared. So I'm going to end up getting 1 million equals 250 times v squared. So let's get v squared isolated, right? That's going to give me 4,000 is v squared. And so, is that right? Oops. Oops. So when we actually end up getting v, we end up getting about 63.25 is v at the top. Now, one small thing. At the very top of the roller coaster, we're going to have normal force and weight pointing down. So we're going to basically say that we have Fn plus mg 500 times 10 equals 500 times v squared divided by the radius. That's going to end up being Fn plus 5,000 equals 500 times 63.25 squared divided by our radius, which is 25. When we actually isolate Fn, we'll go ahead and do that now. We end up getting 85,000 newtons of force. Do I have that right? Sorry, 75,000 newtons of force. All right, that is page 3 of the exam.